Hi, so today I'm going to give a brief overview about word embedding models and demo my program that I made, and you can find the tutorial for in my Medium article in the description below. So first, I'm gonna get started. What really is an embedding model? So, an embedding model is a way for large language models, or it doesn't necessarily have to be large language models, but large language models, how they truly understand words, or like quote-unquote understand. So how they do this is they take a word and they encode it in a vector space, or they take a word, turn it into a vector, and in the vector space, the dimension or the directions and the magnitudes of the vectors may convey some sort of semantic meaning. So in this example right here, as you can see, we have up here grandfather, man, and boy on the left right here. And as you can see, we have woman and girl over here on the right. And so it's easy to see from glancing at it that maybe this direction right here conveys some sort of male definition, or like these words are all masculine, right? Pointing in this direction. Whereas on the other hand, in this direction right here, this may convey some sort of like female connotation, because woman and girl point this direction, which is a different direction than grandfather, man, and boy. And as you can see in the middle is adult, which can be a male or a female, so it points straight down the middle of the male and female words. And so it's easy to see that the directions really do play some sort of significant role when classifying or giving definitions to these words in terms of a model doing it. So, however, 2 dimensions, as you can imagine, is nowhere near enough to encode the meanings of all the English words, or like at least a lot of English words. 2 dimensions is nowhere near enough. Right, so typically large language models use a lot more dimensions. I don't know exactly how many, maybe like 512, possibly more. In my program, I use 128 dimensions. So now I'll get into actually how we are able to turn words into vectors. And really the magic happens in what's called an embedding matrix. So the process is we have a word and we run it. Our word is 1 hot encoded, right? So my program's vocabulary size is roughly like 15,000. So imagine we have a 1 hot encoded word. So maybe our 1 hot encoding is like 10000, and this is size 15,000. And so we run this 1 hot encoded vector through a matrix, right? And this matrix is vocab size by your word embedding size. So mine is 128, vocab size by 128, and this will turn this into a 128 dimension vector. And this is the embedding vector, as I went over before, this is the word embedding vector. And so really, we just need to train this matrix to correctly transform words to give them semantic meaning. And so we can do that with gradient descent, we will do that with gradient descent. How we train our model to have an embedding matrix a correct embedding matrix is we're going to take our data set. So a data set should be very large. Mine's kind of large, I guess. 2,000 sentences. It's okay, I guess, but it works. So we're gonna take a sentence. So I guess I'm gonna take this sentence right here. I'm gonna take this sentence right here. I'm feeling rather rotten, so I'm not very ambitious right now. Okay, and so we're going to use a technique called continuous back of words. And how this works is we're going to go through the sentence. We're going to first go to I'm. We're going to remove I'm right here. And then we're going to take the context surrounding it. Now, to not make the training time ridiculous, it's already pretty ridiculous because it's this is 15,000 words, but to not make it totally ridiculous, we're only going to take the 3 words before our target word and 3 words after. So since I'm didn't have any words before, we're going to take the 3 words after, feeling rather rotten, and that's our context. So we're going to remove the rest of this. So what the model sees is blank feeling rather rotten. And so what it will do is it will turn feeling rather rotten, will turn the context into a vector. And how it works is it just takes the one hot encoding of feeling, the one hot encoding of rather, and the one hot encoding of rotten and adds them together. So effectively, you'll just have a vector with 3 ones. So we have 1, 1, 1, 0, dot, 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 0. Imagine these are the indexes for feeling rather and rotten. Oh yeah, by the way, I should mention that we have a map of words to indexes, and we created that when we made our vocabulary, and we have a reverse mapping as well. So now that we have our context vector, we can run it through our embedding matrix and produce a 128 dimension vector embedding, word embedding. And now the way we train it is we are going to want to have our model try to predict what word is the target word. So it has the context, it has the vector for the context. So now using this context vector, can we predict what goes into the target word? The answer is maybe. So we take if you are familiar with classification tasks, like if you've done the MNIST dataset, that should give you a helpful intuition on how we can take our context embedding and predict what word that belongs in the target word. So the answer is we need another matrix, the de-embedding matrix, and this matrix is size 128 by vocab size. And what this does is it takes the context embedding, turns it back into a vector of 15,000, or however many words you have. So the reason why it does this is because it wants to predict what words are likely to be in the missing target word. And so we'll transform our context, turn it into a size 15,000 vector, and then softmax it to get probabilities, of each word. And if you're unfamiliar with all this, I suggest watching 3 Blue 1 Brown series of neural networks. So now that we have our vector of probabilities, we can use the softmax and cross-entropy loss backpropagation to train our embedding and de-embedding vectors. And so, as you can see in this code, that's exactly what's happening. So we first get our context vector, we run it through our embedding vector, or embedding matrix, we run it through our de-embedding matrix, we softmax the result, and then we use backpropagation to update our embedding and de-embedding matrices. So that's really cool. And so I'll just provide some examples of our model learning that similar words. So in my article, I provided a few examples. Let's just run them in real time right here. So we have he and she. So how my testing really works is we just take 2 words from our data set and we print the projection of them. So a projection closer to 1 means that the words are more similar. A projection closer to 0 means they're not very similar, and a projection that's negative means they're anti-similar, which means that when one of them shows up, the other one is likely not to show up, or they have some sort of negative correlation. So if I print out the similarity of he and she, we get 0.835, which is very similar. And in our data set, the semantics of he and she are not very relevant. Like the semantic difference between he and she are not very relevant. They're mostly interchangeable in any instance of them in the dataset. So that's why they're very similar. Our next example is think/feel, or think and feel. And in our dataset, these words are used very similarly. You could say, I feel like I am going to fail. Or you could say, I think I am going to fail. And that's why they're very similar in our dataset. No, not fail. Okay, so if we print out the similarity between these two, it's 0.81. And so that means they're also very similar. And need and want are also very similar words in the data set. So if I print need and want, so if I print out their similarity, it's 0.56, which is still far above. If I don't load our existing model, the similarity is only 0.05, which is basically just random. So you can clearly tell that the model that I trained has learned there is similarity between need and want because of the 0.56 similarity score, as opposed to the 0.05 it started at. So moving on to guess and think. So these two words are also used very similarly. So like, I think I will fail can also be, you could also say, I guess I will fail. Not exactly the same, but used very similarly. And yes, so they have a 0.772 correlation, or similarity score, which is very high as well. Okay, and so yeah, those are some of the most commonly used words. I think like feel is used a lot, yeah. Think is used quite a lot as well. But words that aren't used as much still are beginning to show some sort of sign of learning, or the model is still showing some sort of sign of learning. So sad and unhappy right here. Unhappy is not used very much, 8 times. Sad is used 18 times. So these words are used less often, but they're still beginning to show some sort of similarity. At least the model's beginning to understand some sort of similarity because their score is 0.359, which is still much higher than if you started with a random model. It would be like less than 0.1. Okay, so yeah, and we also have mad and angry. We can just demo that as well, I guess. Yeah, 0.35. So you can see the model is also learning that mad and angry are quite similar. Now, let's choose 2 random words. Let's choose 2 random words and see if they have anything in common. I don't think we use apostrophes in the data set, so we're going to... Wing and flower, are they even in the data set? Okay. Okay, wing is not in the data set, so we're going to choose 2 different words. Front and butt. Okay, surely these are. Okay, yeah. So if we choose front and butt, so obviously these words don't, there's really not much similarity between these words. So yeah, the correlation or the similarity is not very high, or it's even negative, but 0.089, not very high at all. And the model knows that these 2 words don't really have much similarity, so scent kill. Well, mine air. Is air used? Air. Okay, so we can use mine and air. And as you can see, 0.055. Really not much similarity, and the model has learned that these words are not very similar at all. So yeah, that does it for this demo and the brief overview of an embedding model. My article is linked down below if you want to recreate this model, and thank you for watching. And